In this presentation, I will present you the key features of the libraries, and then I will introduce you to 4 of our recent references, and then we'll see the perks of the library. The library, Quetzal, provides a powerful data structure that can handle all the relevant data to transport models, such as networks and demand matrices. It also provides methods for processing this data. These data and methods are structured in a consistent object model, which means that the consistent object model is used as a framework to ensure that you can chain all the data and the methods in a seamless modeling workflow. And there are automated tests of the integrity module and the reading and writing methods of the IO module that consolidate this framework. Among the methods provided by the library, I would like to stress 2 groups. The first one is a preparation suite, which is a collection of algorithms dedicated to cleaning and resizing the transport input data, such as networks and zonings, according to the model's purpose, and in order to make it fast, clean, and light. And the second group is the transport suite, which gathers all the algorithms required to build a classic 4-stage model, including the trip generation, the trip distribution, the modal split, and the assignment. Some of you already know what a 4-stage model is. Some of you may don't know, so I'm going to explain it really quickly. When you want to do traffic forecast for your city, you will want to simulate one's choice regarding transport, and it comes with the first choice, which is the generation. Where will people start their trip? If I'm speaking for myself, I will start from my house and then maybe go to my work. So when you estimate the number of trips leaving a zone and going to another zone, you will start with the number of people living in the emission zones and the number of jobs in the destination zones. That's called generation, which is the step where you evaluate the number of leaving and arriving trips to each zone of your model. Then comes the distribution, when we say who is going where. So I'm going to my job, which is really nearby, and I'm less likely to go to a mall really far from my house. So this is the point where we match the productions with the attractions, saying who is going where. This is called distribution. Yes, I've got a message.
I think it was just someone wanting to join the lobby.
Okay. Then, when we know who is going where, the next step is the modal split, where the user chooses the mode of transport that he is going to use. I'm really into public transport, so let's say I'm going to use the public transport anyway, and I don't have a car. And then the last step is the assignment, where we all choose our very itinerary within this mode, and we assign the number of trips to the transport lines or to the roads. So this is the really basic 4-stage model that have been developed in the 70s and which is still used nowadays. And Quetzal gathers all the algorithms that are required to build these 4-stage models. However, 1 second. Although Quetzal provides the tools to build a standard four-stage model, we often use another framework to better model multimodality and ensure consistency between the model split and the assignment. In this framework, trip generation and trip distribution remain the same as in the four-stage model, but then the Pathfinder step enumerates all the paths of all the different modes, public and private. Then the utilities and the probabilities of this path are evaluated in the logic step that not only does the model split, but also the weighting of the various itineraries of each public mode. Given that the output of the logic can serve as inputs for upstream steps, such as Pathfinder or distribution, this sequence is flexible. Loops are used to model these retroactions, and this topic is developed later in the presentation. The generation and distribution of Quetzal are similar to the generation and distribution of Quetzal are similar to what you find in a mainstream four-stage model. So in this presentation, I would like to better explain the Pathfinder and the logic steps. The Pathfinder of Quetzal the Pathfinder's aim is to enumerate a comprehensive set of relevant paths for various combinations of public and private modes. It does so with a collection of independent pathfinders, Pathfinder algorithms for public transport, motorized private vehicles, such as cars, and the many combinations of private and public modes. Regarding the public transport, Quetzal provides 4 pathfinders. The simplest one is a fastest path only based on Dijkstra shortest path algorithm, which returns just one path for each origin-destination pair. The 3 other ones return a set of optimal paths for each origin destination. The first one, the iterative pruning algorithm, returns the best path for every combination of public modes. The second one, the optimal strategies, sees a path as a flexible strategy to reach a destination and returns for each destination a set of relevant connections with according probabilities. Both are frequency-based. And the last one, the connection scan algorithm, was implemented to model timetable PT public transport offer as opposed to frequency-based services. And it returns a Pareto optimal set of paths with the fastest PT option from every origin to every destination, calculated for any wished departure or wished arrival time. That's for the public transport. The cars and the other motorized private vehicles, such as lorries and motorcycles, are assigned with a highway procedure with capacity constraints. And the park and ride algorithm performs both a public transport pathfinder and a road pathfinder, and then combine the trip legs at the location of the incentive parking facilities. Once we have generated all the paths, we can feed them to the logic step. The nested logic or multinomial logistic regression is known for its use in the model split of the really mainstream four-stage model. Its practical implementation is the following. It starts with an ascending utility aggregation where the utility of the various modes is aggregated by nests. In this example, and then there is a descending probability estimation. In this example, that means that the utility of the tram and the utility of the subway are aggregated to calculate the utility of the rail. Then this combined utility of the rail and the utility of the bus are aggregated to calculate the utility of the PT, of the public transport. Then, in a second phase, the probability of the public transport is shared between the probability of the bus and the probability of the rail based on the utilities that we had calculated. And finally, the probability of the rail is shared between the probability of the subway and the probability of the tram. This is the basic implementation of the nested logit when we're talking about model split. In Quetzal, we not only use the nested logit for the model split, but also to calculate the probability of every itinerary of each mode. We achieve that by adding a level to the nested structure. In this example, we aggregate the utility of all the itineraries of the tram to calculate the combined utility of the tram. And then the mode utility aggregation and mode probability estimation is similar to the model split example. And finally, the probability of the tram is shared between the tram itineraries based on their utilities. At the end of the logit, each itinerary has a probability. This probability translates in a number of users for a given demand matrix. And the travel time and the overall activity of the public or private itineraries depend on this number of passengers. Say for a road, if there are many cars in this road, it will be slower and the utility will be lower. For a given origin destination, if most people choose to use their cars, the road may become crowded. Then some of the car users may want to change their itinerary or mode of transport based on the crowded travel times. After this new choice, the congestion may drop drastically, and some of the users that had switched to public transport may reconsider their choice. This is why we need loops to achieve some kind of equilibrium, and this loops goes on until we reach what's called Wardrop's user equilibrium, where for each segment of demand for anyone, the perceived attractivity of all the itineraries of an origin-destination couple are almost equal. Then no one can improve his utility, his travel time, by changing mode or itinerary. Quetzal reaches Wardrop's equilibrium with the method of successive averages that is used within the congested road assignment, known as IRA procedures, or in loops between not only the assignment, but also the pathfinder and the logits in order to comply with capacity constraints in the road network, but also in the public transport lines or at the incentive parking facilities. So that was all for the key features of Quetzal, which is a library which provides tools for data pre-processing and resizing as well as transport modeling. Although four-stage models can be implemented, it is often used in a customized sequence with the pathfinder and the logis at the end of the sequence. And in the scope of the customized sequence, we implemented state-of-the-art algorithm in the pathfinders, and we design new ones for our purposes. I'll put some references for the algorithms that I explained really briefly. So this is the paper